No mai haere mai, tēnā koutou e te whānau arorangi. My name is Adam Stevens. I am a research fellow at the International Centre for Radio Astronomy Research in Perth, but I'm also a member of the ASA Sustainability Working Group and a member of the international organisation called Astronomers for Planet Earth, where one of our key missions is to spread the good word on action on climate change, both in the sense of educating the general public and reaching out to other astronomers and finding ways to reduce our own carbon footprint. And it's through my membership with these organizations that we've set up this special seminar today by Jürgen Knödlseder. So it's my pleasure to introduce Jürgen. Jürgen studied at the Technical University of Munich and the Max Planck Institute for Extraterrestrial Physics in Garching, and then later moved to the Institute of Astrophysics in Paris, and subsequently to IRAP in Toulouse. He's been a CNRS staff scientist since 2001, primarily works in the field of gamma ray astronomy, including data analysis using instrumentation, topics such as nucleosynthesis and antimatter, and most notably was chair of the consortium for the Cherenkov telescope array for 9 years, and recently stepped down from this role to focus on sustainability issues. So about 6 weeks ago, Jürgen posted a paper on the archive, which is the subject of this talk today, on the estimate of the carbon footprint of astronomical research infrastructure. And this is a very important topic because I'm sure, as Jürgen will tell us, it complements work that's been going on in the last few years across the world, including some work that I've been involved in here in Australia. We've been trying to quantify what the environmental impact of our research field is, and then trying to come up with solutions about how we reduce that. And the work that Jürgen's led indicates that the amount of the resources that we invest into just establishing key infrastructure like telescopes can outweigh the rest of what we do in our jobs, from travel to supercomputing, in terms of the effective carbon footprint that it has. So without further ado, Jürgen, I would like to hand over to you, and please take it away. We'll be sure to have a Q&A session.
Thank you, Adam, for this great introduction. So I can really go immediately, basically, to the first slide. All this work came up because we started something like 2 years ago to think also about making a carbon footprint estimate of our lab, so IRAP in Toulouse. So we are a very big astrophysics lab in Toulouse, working on planetology, any kind of space observations, infrared, gamma rays, X-rays, and so on, and basically building also a lot of hardware. So what we wanted to do is to make a fully comprehensive carbon footprint estimate. So going a little bit beyond what others did before, in the sense that not only estimating our travel footprint and electricity and heat and so on, but really trying to cover everything that we do. And here you see on this slide the outcome of that. You see in this pie chart the different contributions to our footprint. And what is really new in this estimate compared to other works before are several parts here. So this orange thing, this is the use of data from space observatories, and you see visually already this is the biggest part in this pie chart. Here, this is the use of data from ground-based observatories. This is the conventional professional travelers going to conferences, but also preparing our observatories and so on. So all working meetings. And this is also interesting, and I think new and was done the first time for an astronomy lab. All the goods and services that we purchase, we buy a lot of material, or we outsource also things for buying, building hardware for instrumentation. And so you see that when you just add up these things, I mean, this is already a very substantial fraction of the carbon footprint. So we really have to worry about our infrastructures, which is somehow the outcome of our paper and also of our work at IRAP. Now, when I speak about research infrastructures, what I mean is, of course, all our space telescopes. space probes. We have also, for example, in our lab, plasma physics and of course planetary probes. Participate in probes on Mars, for example, and all the ground-based observatories, optical, infrared, but also radio, and eventually other ground-based observatories. So the question is, of course, why should astronomers worry about their footprint? Well, first of all, I mean, astronomy wouldn't be possible without any infrastructures. I mean, they are really essential to our work. And the method that we employed, this is the so-called bilan carbon method. We got, by the way, all the co-authors got a training in 2020 on applying this method. And in fact, according to this method, what you have to include in your carbon footprint is all the fluxes that go into your organization or go out of your organization and for which you are responsible, or on which your activity depends. And in fact, it's a very simple question to ask: will your activity be impacted if you remove a given flux? And it's obvious, if you remove astronomical infrastructures, we just close our shop. So, but in addition, I mean, that we even also have some responsibility, because first of all, it's us who invent these infrastructures. And for example, specifically in our lab, we contribute to building and eventually operating them. So we have also really a share and a responsibility. And of course, if we won't be there, there won't be any astronomical infrastructures. So it's really very obvious that you have to consider this footprint. Now, the method that we use is a very classical method of how to estimate the carbon footprint here. So first of all, you have to define the boundaries of your exercise, basically what you take into account for your carbon footprint estimates. And what we started off is going through all infrastructures that were used by researchers of our lab in 2019. 2019 was our reference year. We tried to include all emission scopes. So these are different basically levels or kinds of contributions, like direct energy use or direct emissions coming out of your observatory, but also all the upstream carbon footprint, all the materials that go into your observatory. And then in the temporal domain, it's basically, we try to cover the construction period, eventually the launch if it's a satellite, and then also the operation period of your observatory. And then what you have to do is you have basically to sum over so-called activity data, so amounts of stuff, and multiply them by emission factors, which is basically how much tons of CO2 are emitted by a unit of amount of stuff. And the amount of stuff can be anything that you like in principle in the method. What we used here is essentially a cost-based analysis. So we have here as activity data mission cost. For space missions, we used a second method for cross-checking based on the payload weight, so the weight of the satellite of your space telescope, if you like, to make this estimate. And then, as I said, we try to find data for construction and operations of the facility. And here are these emission factors that you have to factor in: how much tons of CO2 per mega euro, so we worked here in euro, of course, and or how much tons of CO2 spent per payload kilogram. And I also want to emphasize that we not always were able to meet our boundaries that we like to have. For example, sometimes we didn't find cost data, and so we just left them out, and formally then this gives you only lower limits to the truth. Now here the emission factors. Here, these are the first table here shows the emission factors that we used in our work. And how we got these factors was basically by looking into existing carbon footprint estimates. And they are very rare. They're very difficult to find first, but even if you find them, I mean, they're basically none. I mean, we were very happy to find some work for space missions, but that's only a single work that we found here. And for ground-based observatories, there were several works we could base our analysis on. And so it's a bit richer and maybe a bit more consolidated, these numbers. The interesting thing is when you can compare these numbers here to numbers of other activity sectors. I mean, there are these monetary emission factors for basically all kinds of activity sectors. And here, just in the second table, I wrote down a bunch of numbers that you can find in the carbon database in France from the ADEME organization. And you see that, in fact, our values here are specifically, I mean, the cost-based values are on the low side of this table. And this means that at the end, I mean, the per activity carbon footprint is relatively low, in fact. And this also means that it will be very challenging to get these numbers lower. It means it will be very challenging to decarbonize actually our activities. Now, in fact, the most important part of this work actually was to find activity data, or basically finding, in fact, cost data for satellites and ground-based observatories. I mean, not everybody is open about the price of the facilities, the price tag, and so sometimes really it took a lot of time to find just a single number in these tables that you see here that summarize basically all the data we found. I mean, of course, finding satellite mass data is pretty easy. You just go basically on Wikipedia, or can go on other sites. They confirm basically on all different sites. But cost data is the difficult thing. And also sometimes it's not clear actually what these cost data that we found actually includes. So very often, for example, they don't exclude mission extensions, and they never include, for example, upgrades for ground-based observatories. So typically what we have here is the initial construction cost and the current yearly operation costs of ground-based observatories. So this means that also in this aspect here, our results are lower limits to the truth. And as I said before, if we didn't find data, you see here some blank parts in this table. We just left this data out, which makes it even more lower limits. And then as a detail, we corrected for inflation in all this data to put them all to the same reference, 2019 economic conditions. So this gives you a big table at the end where you have for each facility the carbon footprint. And in fact, in total, we had 85 facilities in our table. The way how we got these 85 facilities basically was just by looking in all publications of our lab in 2019 and trying to extract from the publications the infrastructures that were used for writing these papers. It turned out later that, I mean, we missed some of the infrastructures that were used, but this is just how we constructed our initial list. And as you see, I mean, we cover quite some fields and in fact, a quite large list of infrastructures. So this gives us the total carbon footprint of a facility, and to get the annual footprint, we just divided the life cycle footprint by the lifetime of the space mission or the observatories. And if the mission was just started recently, we said, okay, let's divide at least by 10 years. Otherwise, we would get a very large annual footprint that would by time dilute at the end. So I also want to emphasize here that you don't have to take these values literally. I mean, the uncertainty on individual values is rather large, and this is related to the method that we just use the money flows associated to a facility. So be aware that the real carbon footprint, typically it's 80% what is recommended to use as an uncertainty, and that will be used in this paper. And so the real footprint could be 5 times lower or 2 times larger. But of course, if you sum these things up, the relative uncertainty becomes smaller. Now, one exercise that we played with this table is trying to put these the carbon footprint in perspective. And the perspective was basically, what is the science output of a given facility, or what is the footprint of a given facility divided by the number of authors. The way how we do this is basically by making queries using ADS and just looking for the name of a given facility in a paper. So it's a good kind of citation index also, if you like. And we up to 2019. So when you do the game and you plot all your numbers, that's what per paper, and on the right the carbon footprint per author. And of course, if an author signs several papers for a given facility, the author is only counted +1 here. What you see first, there's a large scatter in these numbers. I mean, I had to use a logarithmic scale so that you can see anything. So it really depends on the facility, what the typical footprint is per science paper or per author. What you also see is at the beginning, of course, these numbers are high because basically the number of papers after a few years is low. So the denominator is relatively high, but this levels off after 1 or 2 decades, and then creating some scatter here around an average. And this average, and then here we use the mean because I mean this distribution is relatively skewed. So the median values here for the per paper footprint is around 22-24 tons per paper. So you see already here how significant the footprint is. And when you do it by authors, there are of course a bunch of authors on each paper. Gets even density gets smaller. So here you have typically 10-13 tons per author for a space mission, and for ground-based observatories, apparently there are more authors on these papers on average. The result is 6 tons per author. Now you can also sum all the numbers up, and that's what we did here. And the first interesting thing is when you look at the space missions, whether you use the cost-based estimate or the mass-based estimate, you end up in the same ballpark. Of course, the numbers are not identical. I mean, this would have been very surprising, but they are not so different. Of course, I want to emphasize, I mean, we didn't find cost data for all missions. So here, this is only 40 out of 46 space missions that are counted here. But even if you add these 6 more missions, I mean, this makes these numbers a bit higher, but not so much. So coming from 2 very different routes, one based on how much your space mission costs and the others how much it weighs, you get very similar answers. Here in our table, the footprint of ground-based observatories is smaller than space missions. But this can be explained because, as I said before, we are a space science lab and we are mainly working on data analysis of space missions, which explains why the ground-based observatories weight in here less in the table for our lab. And at the end, well, all this sums up to 7.8 million tons of CO2 over the lifetime of the infrastructures. And when you look at the annual footprint, it's almost, well, it's even a bit more than half of a megaton CO2 per year for all the infrastructures. Now, we recognize that, I mean, this list is quite long and we can in fact extrapolate from our list to the world inventory of all astronomical research infrastructures. And the way how we did this is using a bootstrap method so that we can also assess an uncertainty related to this extrapolation. So the idea is the following: we have here our list of research infrastructures that give the 7.8 million tons. And then we bootstrap from this list to the total number of infrastructures that exist in the world. And when you do this several times by using a random number generator, you get a distribution because you sample basically different infrastructures from your list. And this gives you a distribution of carbon footprints that could represent the world carbon footprint of research infrastructures. We also did a modified version of that because we recognized, when you do the sample, you sample a given infrastructure actually several times. But there are infrastructures in our list that are just unique. There's no equivalent in the world. I think, for example, about the Hubble Space Telescope or the ALMA Observatory and so on. And they have, of course, a huge carbon footprint. So we said, okay, let's take the huge infrastructures out, of course, count their footprint, but only once, and then sample all the others. And this gives you, of course, a little lower footprint overall and a more narrow distribution, although because your scatter becomes smaller. What we also did to remove bias is to divide all facilities into broad categories, like all the solar science facilities, plasma physics, astrophysics for space observatories, optical telescopes on ground, and so on. And for each category, we determined the number of facilities to get basically the number here we have to sample. That existed in 2019 in the world. And of course, the assumption here is that we assume that the 85 facilities in our list are representative. Okay, so this is here the outcome of our extrapolation result. And what you see here basically in these graphs are the different contributions. So space missions, green is ground-based observatories, and red is basically if you add both up. And then you have the filled histogram. This is the cost-based data, and the open histogram here is the mass-based estimates. So this gives you a kind of sense already of the total numbers here. So the total footprint, we are now between 20-25 million tons. If you use this original extrapolation method, and this goes a bit down to around 20 million tons if you use the modified extrapolation method. So this gives you also a sense of the possible biases that are in this kind of extrapolation. So summing all this up in a table, this is the numbers that you get. For the space missions now, you have 7.4 million tons, and now it's the ground-based observatories that dominate 14.2 million tons. It's just because there are so many of them. Every university almost has observatories hanging around. And of course, every country wants to have its own infrastructures and so on. So, the list is really large, much larger than for space missions. And so when you sum up all these numbers, so you get 21.6 million tons if you use the initial bootstrapping method, and if you use this modified method, the total footprint goes a bit down, 19.1 million tons, but not very much. And and the annual footprint is around, let's say, 1 megaton. So you see, before we were 0.5 megaton per year, and now we are 1 megaton per year. So the extrapolation basically doubles the annual footprint of the missions we had in our initial list. Now, what we also did, and of course this created quite some excitation, because it says, well, your footprint is, and well, this was not the primary purpose of this exercise. We wanted to make a comparison, and we wanted to compare, of course, the footprint to estimates that were done before. For example, also the estimate that you did in Australia. And so we want to compare, how does it compare to flight, supercomputing, and so on. So we can do this first for our lab. We just divide the IRAP footprint by the number of IRAP scientists. And this gives you 27.4 tons per year per scientist. But as I said before, we missed some of the facilities we use at IRAP, and we looked a bit into that. We didn't correct for this afterwards, but we just made an estimate of what the correction would be at the end, and it turned out to be around 20%. So, I mean, this number should be plausibly 20% higher. And when you use the bootstrap method that I just explained before, and you divided the annual footprint by the number of astronomers in the world, and here we took a number of 30,000, which is maybe an upper limit, but it's around the right number, you get 42.8 million tons, sorry, 42.8 tons per year per astronomer. And when you use the modified bootstrap method, it goes down to 35. So we just said, okay, let's take these different numbers and let's just speak about a plausible range of per astronomer footprint. And here you have the number 36.6, and the uncertainty here includes all uncertainties related to the differences in these numbers, and also here the uncertainties for the individual numbers. Again, I mean, this is a conservative estimate. I mean, we always try to be conservative so that we don't overestimate the footprint at the end. I said we left out some data here. We used here 30,000 astronomers, which is maybe an upper limit. So we try to be conservative in all places. Now, the real discussion starts, in fact, here. So, and the question is, of course, so what can we do about that, and where do we have to go? So, what I depicted here on the left is it's just basically a rough estimate of an astronomer's footprint, and that I took here a number of 60, but of course this depends very much where you are located. And if, for example, your lab has solar panels and all these kinds of things. So what you have is you have really a big fraction of your footprint is related to our research infrastructures. And then, of course, you have other stuff here like professional traveling, the heating of your buildings, and the material that is purchased at your lab, and so on and so forth. And then, of course, an astronomer has also life, sometimes a life outside of astronomy, and so has also a lifestyle footprint. So formally, you get a number of around 60 tons per year per astronomer. And of course, we all know we have to ramp down quite importantly. And I won't discuss now or say we have to ramp down to this figure. I mean, these are just figures that are basically circulating in the literature. It's like every human has to end up in 30 years with 2 tons of footprint. Or you can say, well, all societies have to ramp down by a given factors, and these factors depend if your country is carbonized or not carbonized in terms of energy production. And others argue, I mean, you can also base the target on your responsibility in climate breakdown, because, I mean, CO2 stays in the atmosphere. So what counts is not what is emitted today, but what was emitted over the last 200 years, basically. And when you do that, I mean, I even did put a number here. I mean, it basically means global north is 0 and global south can still ramp it up. But whatever target you choose, it will fundamentally change, of course, how we do astronomy in the future. Of course, I mean, when you go in a discussions like that, you have to think about our societal impact, but you also have to think about what are the needs of the humans and what are the wants, and also how you can distribute this burden on the entire humanity in an equal way, and think also about the responsibility behind all that. Also, and this is not in the paper, but I mean, of course, it's always interesting to look beyond, because I mean, now here we're pointing somehow to astronomy, but of course we are not alone. I mean, every field that uses research infrastructures may have a similar problem. For example, CERN, so the big particle accelerator in Switzerland, they have put out a carbon footprint assessment, but it does only cover scope 1 and 2 of the footprint. So it's not a full footprint assessment. But when you look only at scope 1, which means is what are the greenhouse gases coming out of CERN? And of course, there's no, this doesn't include the electricity you use to power CERN. It's just the gases that come out. It's 190 kilotons per year, 4 years where CERN is actually, where the LHC is actually operating. And this is just due to the gases they use for the particle detectors and for the cooling of the infrastructure. So this is already a huge number, and only a few factors, a factor of few of our total. And the second exercise that I did here is I looked in the S3 roadmap. So this is the roadmap for European research infrastructures. And the interesting thing is there that it contains activity data, so construction and operation cost data. So it's pretty easy, basically, to use this data and say, okay, let's use the same factors that we found for astronomy for ground-based observatories, because all these other things are ground-based. And this is by sector: energy sector, environment sector, health and food, physics. And here I put out the astrophysics. So this is the thing I just talked about, the astrophysics footprint. And this is all the remaining physics, the particle detectors, solid state physics, and so on. So you see, I mean, all the other domains also have issues. Physics is in fact the domain that has the biggest issues, because formally you have to add this here on top of that. So this is really the biggest bar. So of course, all other communities have to make the same kind of assessments to see where they stand. And now also, I mean, when you do a carbon footprint analysis, and at least the method we were taught is only complete if you devise an action plan. And we said, okay, let's also do that step, and also let's do that step in the paper. And of course, and here, when you take an action plan, you take decisions. So it's of course our proposal, and this is certainly something we can and have to discuss about. So the first thing is that each plant or existing facility should perform an environmental life cycle analysis. And this is very important because, I mean, as I said before, I mean, our analysis is just based on these emission factors that are based on a very few assessments that exist. So eventually, I mean, there is eventually some bias there. And also, I mean, the monetary approach has a very large uncertainty. So to get more robust numbers, you need to make really a full environmental life cycle analysis. And then once this is done, facilities have to make also their action plan. There are some facilities that are doing that. I come to this later. And should also, I mean, eventually these kind of analysis are needed if you want to inform, for example, the implementation decision on the footprint of your infrastructure. And very important also, I mean, this analysis should be made public. And I say this because, for example, the European Space Agency, ESA, is doing these kind of things. You see here, for example, an illustration of that, but they don't publish numbers. So this is really astonishing. What they publish is relative contribution. So you know what phase of the mission, for example, is contributing what fraction of the footprint, but you don't know if it's 1 ton or 1 megaton. And I think I mean, the reason is very obvious why they don't publish these numbers, because these numbers are pretty high. But what they do is very interesting, because I mean, this is only the carbon footprint here, the first line, but they look in many other things like ozone depletion, water pollution, and so on. And this is what I mean by environmental life cycle analysis. So not only look at carbon, but look at everything that impacts the environment. So once once this is done, of course, you have to devise a quantified action plan to decarbonize as much as possible the existing stuff. So, and this includes even space missions, because what exists there is operating centers and ground stations. You have, of course, get the data, and most of the operations footprint of space missions, or basically all, is related to these ground stations. And there are examples, and I take here ESO, not to point to ESO, but to show that they are really showing the way what should be done. So first of all, they have made an operations footprint assessment, and the outcome of this is 28 kilotons of CO2 per year. And they announced an action plan that you can find on the web. Here is the link to this action plan. And they don't say over how many years it runs, but they give the numbers for every action. Basically, they reduction numbers for every action they want to take. And these numbers sum up to a carbon footprint reduction of 4.4 kilotons. So this would, when you just divide this by that number, would correspond to an operations footprint reductions of 16%. It's also very important that these action plans are public. And well, our proposal in the paper is that IOU could hold a registry of these plans. And then, of course, you have to monitor your action plans and see if you are on track and eventually adapt the action plans. Now, the question is, of course, is this enough? And when you look in these numbers, I mean, I showed you for ESO is 16%, and very often when you read about other stuff, it's roughly maybe a 10% or a few 10%. That people are aiming to reduce. So this is good, but it's unfortunately far from the factor of a few that is needed for the next decades. And that's just the inconvenient truth that, I mean, although all these measures are very positive, they are hardly sufficient to get to our target values. Now, a second point, and I think even more important than the first point, is that these carbon footprint reductions will only be effective if you don't add other stuff. And other stuff means constructing more observatories that create more carbon footprint in the future. And I take here the example of the ELT, so the next generation telescope of ESO, and only for the very simple reason, because here cost numbers, carbon footprint numbers are available. So there is an estimate of 63.7 kilotons for ELT construction. I think it's on the lower side of the true value, but let's take this as a face value. So if you spread this footprint out over 50 years, let's say ELT will operate over a long time, it gives you an annual footprint of 1.3 kilotons if you spread it out over 50 years. Now, but of course, you have to operate the ELT, and I don't know, I mean, there's no estimate for the operations footprint. Just to give you a number here, VLT has an operations footprint of 9.4 kilotons. So you see, if you add to this 1.3 kilotons, even a very tiny operations footprint of 3.1 kilotons, you fully annihilate all the carbon footprint reductions that you did before on other things. So it's really questionable, and I think this is really a serious problem, whether you can actually reduce the required carbon footprint reductions by continuing to deploy new astronomical research infrastructures at the current pace. It's a question of pace. If you slow down, of course, you can do it. But at the current pace, it will be extremely challenging. So our conclusion is that we need both carbon footprint reductions and a reduction in the deployment pace. And this is where we come to our plea for low carbon science. So how can we reduce actually the pace? And this is also a little bit a personal perspective, because that's actually what I'm doing over the last 2 or 3 years, that I'm mainly focusing on using archival data, trying to develop also new methods and algorithms to analyze this archival data, analyze data that were never explored. We all know there are data sitting somewhere where nobody really looked into them, or not very deeply at least. Specifically, what I'm actually doing is asking new science questions to old data, because the data is still there, and the science has evolved in the meantime. And actually, you can go back to these old data and see how you can put them into the light of the current knowledge. And you can also try to tackle more difficult analysis of things that normally you never do, because you go for the low-hanging fruits, and also tackle difficult science questions. And then also you have to use our imaginations, because you shouldn't believe that the science, the way how we do science today is the only way how you can do science. Science can be done differently, and also new ideas may outweigh new data. We're always running about the new observatory, you get more data, but sometimes it's maybe even more efficient to just think about the problem and try to solve it by a more theoretical work. So also time to think about physics, or maybe you do it. I'm sure I'm not doing it. I'm more focused on the data. So, I mean, this is also something where you can just spend more time to really think about what actually you're doing in terms of physics, and also be unconventional and explore new roads. And in fact, there are a lot of side benefits in reducing the pace. And this joins pretty much the slow science movement. Maybe you heard about that. They speak about more time for in-depth science, so more reading, more discussions, more collaborations, and more communications also to the outside world, because it's very important that we convene, of course, our finding to the general public. Also, less publication pressure, and this is very interesting. I found this just recently, an article looking into the evolution of the number of publications in science globally, so not for astronomy, but globally. And it's really astonishing when you look at the growth rates. I mean, this was here down to, even before the 16th century. So the 18th century, sorry. So this had already in the past a pretty impressive growth rate of almost 3%. But today we have a 5% annual growth rate in the number of publications. And it's just, I mean, you just are thinking about, I mean, how will this end? I mean, at some point we'll publish basically all day something somewhere. So, I mean, question is, do science in that way if you publish so much? That's of course a big debate that is around, and it's obviously, I mean, if you reduce the pace, you reduce all the publication pressure. And finally, I mean, if of course you reduce the pace, there will be more money available for decarbonization. Today, often you just don't decarbonize because you don't have the money to buy solar panels or whatever. So if you have more money dedicated to that, of course, you can decarbonize what exists. So this brings me to the conclusion, which is really our deep belief. So of all the co-authors, is that we have, in fact, actually the solution in our hands. So the only question, and we can just chat now about that, is whether we will choose to recognize that we have the solution in our hands, and whether we will make use of it. Okay, thank you.
Thank you very much, Jürgen. That's a very informative talk. Now is the time for people on the line to start thinking about their questions, and I'm going to particularly encourage students and early career researchers to stick up their hand and ask something. This is not the normal topic in which we normally work, which means there's definitely no dumb questions. I love to see 2 ECRs popping up their hands, so let me go straight to Katie Jameson.
Hi, Jürgen. Can everyone hear me?
Yep.
Yeah.
Right.
Okay, good. It's the first time I've turned it on today, so like never know. I am currently at CSI Aerospace and Astronomy, and I've been doing a lot helping to lead the diversity and inclusion work. So there's a lot of overlap there in what you've said, and I loved that you brought up the issue of kind of growth, which is similar to kind of our growth economy, and clearly that's driving a lot of these issues, but we're doing it in science too. I was wondering if you or other senior members on this call could speak to how much acceptance you're getting towards this, or real movement on people committing to make real systemic changes to how we're doing science on a day-to-day basis.
Yeah, I mean, this is really the tough point. I mean, many people said to me, very nice work, excellent, we have the numbers, a great thing. But when it comes to the conclusion, I disagree. And of course, I mean, and even, I mean, I look at you, I mean, you're young, I'm not so young anymore. So for me, it's a bit easy to have this kind of discussion, because I mean, I've done my job somehow, and I can now take it easy and slow down. But you're all eager to make new discoveries, new observations, and so on. So for you, it's even tougher than for me. But even the old guys, they all told me, oh, no, we can't slow down. We have to do this and that. And it will be really a challenge. And I think it's really important that the community thinks about that and discusses about that. And hopefully, and that's why also I put up a number of options on what you can actually do, because it's easy to say you stop doing something. But in fact, I very much believe in the thing that you have to create a new story. In fact, you have to invent a new vision, and this goes beyond only astronomy for humanity. In fact, for economy and so on, a new vision how things should be done in the future, and that people say, well, this vision is not so bad actually, and I think that's the only way how you can bring people to go in that direction. Just saying to them stop, it won't work.
Samir.
Hi, thanks, Jürgen. So my question is along the same lines, I think, because I never thought about it in a way that we are developing things fast, because as an observer, we've been waiting for things for years, right? For James Webb since 1995 or something. So for me, like, it looks like we are going to, for example. So my question is, like, for example, in case of Australia, we are in GMT and maybe in the ELT if we allocate in the future. How would we go about cutting the carbon cost there? Is it better to just to invest some money on a carbon bank or something like that? Or like because it's probably impossible to build it carbon neutral, right? Because we have like concrete and stuff, it's always going to be like carbon heavy, and then the vehicles that has to go to Mauna Kea or like Paranal and stuff will be like, so the only way we can do is to neutralize the carbon. So I just want to get your opinions on what would be the best way to go on about this by balancing out our impact, especially in Australian perspective.
Yeah, I mean, you as I said, I mean, just decarbonizing costs already quite some money. And if agencies would be willing to spend more money on decarbonization, this would already be a very good step in the right direction. I mean, we did also some little side work. It now went basically in the supplementary part of the paper about offsetting, because very often you read about offsetting, you should offset your carbon footprint and so on. And actually, the numbers typically, how much it costs to offset typically, these numbers are very much underestimated if you look into a real scenario. And when you think about a real scenario, so not only counting how much carbon goes into a tree, because I mean, there was something else before there in the tree. So what you have to look into is how much additional carbon is sequestered if you plant a tree, and then the numbers become much lower. And when we looked into this, for example, for ALMA, you would basically have to invest half of ALMA's construction costs to offset just the construction footprint of ALMA. And so you see, I mean, these are huge amounts of money that are needed to decarbonize or to offset if you really want to do it. I'm not really a fan of offsetting. I really prefer to avoid in the first place. But if you want to offset, you have to pump a lot of money into that.
Sabina?
I'm going to take my mask off so I'm not some masked human. Thank you so much for that, Jürgen. That was, I mean, it's just wonderful scope and the detail of the research and the conclusion. It's fantastic. It's really interesting to see now where you play these futures through in your mind and you can instantly see the potential conflicts that are coming through as to why people might, you know, reject against this. I mean, I don't know of a single astronomer who isn't drowning in archival data and yet who still isn't planning for more data coming through. And I think we can all see the consequence of that. You've got, you know, individual careers hanging on the line where you're taught that if you haven't pushed the next big thing or put your name on something new, then your career will flounder. And so you've got that incentive to keep pushing for more, even though you may not even want more. You raised it in the talk already, the fact that you've got political aspects of it, the fact that different countries or different organizations might want to have access to their own requirements. So there may already be a disincentivization for collaborations and to double up on an investment of carbon. So there were already all these conflicts going on. And then the question is, how do you combat all of those and also get to these, you know, possible benefits in the future? I guess for me, the interesting thing from your talk was to see, sorry, I'm blabbering on, to then talk about how the carbon footprint then corresponds to scientific output to individuals participating through. And I hate to be the one to raise metrics, but is it the kind of thing where we could see a future where the actual carbon footprint of a scientific endeavor becomes one of the key things that we use from the initial get-go? Can we potentially see a future where it's possible to predict, you know what, this is a spectacular, I don't know, X wavelength mission, but the reality is that the carbon footprint per publication or per scientific endeavor is relatively high, and we can use that as a way of saying, is this really worth the carbon footprint? Is that something that we might even see as possible going forward?
Yeah, I mean, just to echo, I mean, to answer your last point, I mean, that was exactly our point. I mean, in principle, you should think about the implementation based on what the carbon footprint will be. And of course, it will be tough, and I have no clue if we ever come to this point. But at least that's what should be done. Now, of course, you need a systemic change. I mean, it's not enough if you just do in your place changing your work. I mean, I do that personally just also to show the way and just to be able to tell to people it's possible. You can do it in a different way. I must say we are very lucky in France, in fact, in the sense that our agencies, although they don't buy into all this, specifically about the ramping down and so on, but they very much support us in our activities. So we have this, I put the logo on the first slide, Labo 1.5, which is in fact a research federation from all kinds of research activities, so not limited to astronomy, of people who worry about that. And for example, our training was paid by our lab. And we can dedicate research time to these kind of questions in the framework of this Labo 1.5 association. Even for now, our evaluation, because we are regularly evaluated by our employer, they recognize the fact in our evaluation that we work on these kind of things. And I think these are all very important steps, so that this activity already, thinking about the carbon footprint, is part of astronomical research de facto now already in France. So I think this is a very important step. And then this also folds in to the evaluation of careers or evaluation of somebody applying for a job and so on. So if we can really come to this, I think this would be already a very good step in the first direction.
Ron, you can have the next question.
Ron is here, and I'm asking this question because I have an interest in the scientific process, history and philosophy of science. In the end, you showed the exponential growth of publications. People, and the solar price in particular, have demonstrated that across all areas of science, they only flourish when the growth is exponential. So so to kill the exponential growth has a great potential of actually killing the science. The solar price hypothesized that fields that don't have exponential growth have died out. And that's why when you do a study, you always find these exponentials. So that is in conflict, as you pointed out, with carbon footprint issues. And so there is a really serious dilemma. But I would suggest you don't advocate killing the exponential growth because you may have killed everything. Instead, take a telescope like SKA, which I'm involved in, actually demand that they have an operating plan with a minimal carbon footprint. They talk about it, but I don't think they've actually done much.
Yeah, it's in fact, that is an interesting point of view, because I mean, I always hear the people that say, well, the exponential growth is killing us. That's exactly what's going on with climate change. So, well, I don't know. I mean, it's, I'm just thinking that people are dying these days due to climate change. More people will die tomorrow due to climate change. So you have to weigh in what is more important. Is this human life or exponential growth?
Oh, hold it. You don't. But there are other ways you can have one area is we just do less different things, but let there be exponential growth where fields are flourishing.
Yeah, but I mean, for the moment, I mean, there are no signs for decoupling between exponential growth and the impact of this growth.
Yeah, I agree with you.
And then it's also the question, I mean, who decides which field flourishes? Everybody wants his field to be flourished. Everybody wants to have cars, iPhones, all this stuff. So why is our thing more important than the other things?
Sure. Well, because if we don't do something about the carbon footprint, then we have to do something. Now, but you know, if you have exponential growth in something with no carbon footprint, you're okay. But of course, that's probably impossible.
Yeah.
Even though we've just got a couple of minutes left, I want to throw the floor to Natasha for her question.
Thanks, Jürgen, for the talk. I'll be brief to keep the time short. What do you see as the role of large astronomy societies like the EAS, the ASA, the AAS in coordinating actions of astronomers? Or do you see that there's more way of reducing our carbon footprint through, say, funding agencies, you know, going to more of a governmental level or an intergovernmental level? I think Sabina's talked quite well to the fact that individual astronomers have incentives under which they operate, and it's hard for any one of us to put up our hands and say, I sacrifice my career on the altar of reducing carbon footprint.
It's in fact an and. So we need all of that. I mean, for example, I mean, we spoke specifically in the paper about the IRU that they could play a role. Unfortunately, they don't seem to be at all going in that direction. I mean, I contacted them, I didn't get a reply. So there are other societies, maybe even grassroots societies like the Astro for Earth or things like that could become more important. But if your national society, for example, Astronomical Society, is interested in that, and I know in France, for example, it's the case and so on, they can of course also help to drive this process. Of course, then you need the agencies because they have the money, and you see basically it's related to where the money goes and how the money is used. So the agencies are very important. And intergovernmental, I mean, you have this basically when you make a new international observatory, it's very often intergovernmental organization, ESO or something like that, or ESA, but even at lower level. And they also have to go in the same direction now. For example, ESO, they have now really an office for environmental questions. I mean, the real question is the end is, are they doing enough to really cope with the problem? But I think we really need activity at all the levels. And of course, I mean, astronomers won't save the climate problem. So of course, the entire society has to go in the same way. But I think we have a voice. And if we can show that we do it and we are serious about it, others will also think about this seriously.
Given that we're past the hour, I think we'll stop the questions there. Let me just once again say thank you very much, Jürgen, for this talk, and for everybody who's online. If this is one of your first interactions with the subject and you'd like to partake a little bit more in trying to find solutions, our door is always open with the ASA Sustainability Committee. If you'd like to join that, please get in touch with Timea. He's probably the best person to contact about this. And if you haven't already joined Astronomers for Planet Earth, we've got more than 1,000 members across 170 countries or something like that. It's basically the whole world at this point. Yeah, that our door is also open there, and we've got a very active community there. So thank you everybody for joining. I will be sure to share this recording, and yeah, see you around.